great fortune to sit down and have a beer with Sam. I don't know, what was that, 4 years ago, 5 years ago?
Yeah, probably more. St. Louis somewhere, I think.
Yeah. Terrific guy. Sam Ximenes is a founder and the CEO of Astroport Space Technologies. Mr. Ximenes has 30 years of experience in aerospace industry supporting major NASA, DoD, and other commercial and international space programs with subject matter expertise covering space habitability systems, concept design and development, visualization, smart space infrastructure, and facilities planning and project management. Mr. Ximenes holds a Bachelor's of Science in Environmental Design from Houston, Texas A&M, and a Master's in Space Architecture for the University of Houston. He is a senior member of the AIAA, associate member of the American Institute of Architects, and a member of the American Society of Civil Engineers. Specifically regolith operations, which I think I didn't even know that was a specialization. So that's pretty awesome. Also, he has a pretty solid background in lava tube. So if you want to like veer off course a little bit and talk about that, I would like to hear a tiny bit about your lava tube stuff.
Yeah, sure. Right. We're doing some good stuff there.
Okay, I'm gonna go off screen to give you your time. Thanks a lot.
All right. So we're going to talk about what I call from dust to gas. It's the in a framework for understanding the technologies for lunar site development. Everything from understanding the dust to the gases you need to have for environmental control and even habitability that you heard about from Grant's presentation. So I'm going to talk about 3 organizations that I'm responsible for: Exarch, Astroport, and Wex Foundation. And I'll be kind of mixed up a little bit here in what we're doing in those 3 organizations. So first, let me give you a definition of space architecture, what we do when we talk about space architecture. There's planetary surface system architecture, and essentially that is the habitats and the infrastructure you put on the surface for settlement and habitation. Then we have orbital architecture. These are the domains of space architecture. This is space stations and other types of orbital vehicles. And then we have the terrestrial space architecture. This is the stuff that supports the spacefaring activities here on Earth, such as spaceports. So we like to consider ourselves, Exarch here, as interplanetary architects. We have projects on all 3 planets, or we are endeavored to have technology development for all 3 planets. A little background on Exarch. It was been around since 2007, mostly working with again, the spaceport environment. We were part of the team that did the first commercial spaceport in Mojave with Virgin Galactic and Spaceport America. Then we also were pretty instrumental in leading the concept design for the Houston spaceport, and those 2 spaceports have been pretty successful. They're ongoing. So these are realized projects that are happening from what we do. Our latest customer is the U.S. Transportation Command. These are the guys that transport the military personnel and material all around the globe and get forward bases set up and whatnot. They want us to look at the idea of spaceports globally for rocket cargo, for point-to-point rocket cargo in under an hour of time. Our role there is to understand the logistical constraints and the infrastructure requirements for supporting that type of activity. So it's not just the rockets, it's the ground support systems that have to be put in place and understood. So after 2007, through some time of trying to understand our niche in the marketplace and the recent development of the commercial space activities that are going on right now, we spun off from out of Exarch a company called Astroport, which was started last year in 2020, to start doing the civil engineering part of it. So you can think of Exarch as the architects and Astroport as the civil engineers for the construction of lunar surface and Mars eventually applications, and understanding the materials needed for the construction applications and the processes and the methodology for how do you do these civil engineering projects. The other organization is Wex Foundation. This is our NASA Space STEM education group. We believe that it's important to grow this next generation of engineers and aerospace enthusiasts, and anybody can be involved in space. So with some substantial funding from NASA, we've been able to set up 2 programs. One is called ElCats, the Lunar Caves Analog Test Site Program. And that curriculum was pretty successful that we received another grant from NASA to take the new Rolls of Waste program is establishing the program in schools around the nation. We have about 28 schools already established for the curriculum. We target middle school through high school students. And our idea here is to take the framework of the technology we're developing and turn them over to the students to actually help with us some solutions in that regard. So our whole aspect here of what we look at is we have planetary features of pits and lava tubes that serve as the basis of our technology development. So this again is the framework that we circle our technology when we start or choose a technology to develop. How do you access these pits? How do you deal with them in terms of exploration and reconnaissance? How do you actually live in them? How do you use them for habitability? They're substantial in size. The image there on the right side there of your screen is the biggest cave we have here on Earth. It's in Vietnam. It's got a floor to ceiling height of 48 meters. These are larger on the moon and even larger on Mars. So with that, we focus on one particular one called the Mars Hill Skylight. So we think that this serves as a framework and again, a basis for technologies that not only apply to this particular site, but to any lunar pit or lava tube. And the idea here is to understand the site for surface mining operations and eventually, development of the site and what you need to do to put it in place. So eventually get to a point where you have it covered. The dome is just notional. We don't probably see that happening, as Grant mentioned. Probably wouldn't be a clear dome and not as high. But the idea here is to take that site and understand the surface infrastructure requirements for it, where we have, I don't know if you see the cursor here, but the spaceport itself, the landing port, part of it, and it's located behind some geographic feature to help with the plume blast and mitigation of sandblast and your assets that have already been put in place. There's probably more of a developed site later on. And then we have over here the surface mining activity where we're harvesting the regolith and producing with the processing plant for producing the fuels and the oxygens, and then burying for the storage. Nuclear option over here for the power system coming through, again behind some sort of a rim for protection. You have to have it some distance away, and then augmented also with solar arrays and communication towers. And then there's the construction activity going on around the pit as we get to a point where we can do that kind of thing for making it habitable and useful as a place for settlement. Initially, I think that you're going to have just as much surface infrastructure and surface habitats and whatnot as you will underneath the surface as well. Certainly in the first days of the use of the construction, you need to have the construction crews and the way to do the operations of all the machinery that's going to be happening over there. So we have a notional framework for what's the phases of the development of a site like this. We call it Lunar Ecosystem Architectural Prototype, or LEAP-2. And it is a consortium of companies that have come together with us to develop these different technologies. And each one has sometimes we work collaboratively, or sometimes they work on their own R&D. But the idea is to focus it on the technology development on the lunar pits or the lava tubes. And we use this timeline, and timelines are kind of tricky. We never know how the programs are going to go and what's going to happen in terms of the policies. But we use this timeline that in any phase of this timeline, there's a technology that can be used and developed that's going to be useful. And you don't have to start from the beginning to the end. You can go insert your technology development at any point in there. So beginning with reconnaissance missions for remote sensing. We're doing that right now. I think we have, orbiting satellites around the moon, and they're doing all the mapping that we see almost every day now. And then the next phase is going to be the scientific robotic reconnaissance missions. These are the autonomous missions that will go there to explore the pits, explore the site. This timeline, 2025, we probably won't make that. I think the first CLPS lander is one of them is trying to get to one of these lunar pits. I don't know if they'll ever be able to get into it, but in that time frame, but eventually we'll be there. And then we get to next phase, which is the human reconnaissance part of it. This is the human robotics, where the humans come to ground truth what the robots found, to make sure that the pit is even a viable location, and that there's structurally sound for long-term habitation, and it's just like basically human exploration of the pit itself and the caves. And from there, you go into the next phase, which would be more of a long duration stay. The prior phase is probably 3-day missions, short duration missions. When we get to the long duration stay, now we're talking maybe months at a time. We probably have the ability to at this point, a more permanent infrastructure or habitation module that we put in there. Is kind of a notional idea of an inflatable that could be installed for a longer stay. From there, you get into by the mid-century, we'd say that now you get into the construction part of it, the real civil engineering and development, and the clearing out the site and the debris and the access to the tunnels. You have to remember that the pit floor at the pit location is the collapsed part of it. So as the roof is on the top that you're walking on, and you're probably going to be walking down to a bunch of rubble debris to get down into the cave, and maybe it's even going to be blocked before at that point. So you want to clear it out, and you want to start putting in your infrastructure for long term. And then I think by the end of the century is when we start talking about real long term, sophisticated mobile, hundreds of people living in a base. Well, we covered the pit. The idea is to get out, and I just show here a bubble dome here, but that's probably not going to be that high. You don't want to get bombarded by the big target for micrometeorites. It'll probably be a lower profile, and maybe who knows if you could even have transparent materials. But at that point in the century, what materials will be developed by the time we get there? Maybe there could be transparent materials. They're also radiation protective as well. But again, it's just notional. The idea is to show that we want to cover the pit. And the reason for that is we want to be able to get out of the suits, get out of the cans, and have more room to move around, so that you have more ability to be able to be a real citizen that doesn't have to be confined to these confined suits and modules. I have a movie here. It's probably too long. I'll skip it right now, but you can go to our website. You can see it there. This is a kind of a lunar construction scenario. Let me go to the technology we're working on right now. So this is our first one of our first technology developments. We want to learn how to design our equipment and our hardware for so that we understand the environment in terms of the dust. This little measurement instrument is measuring dust accumulation rates. It's a small little instrument, fits in the palm of your hand. We want to get on the CLPS mission. It uses a technology that's pretty mature called QCM, quartz crystal microbalance. And what it does is measures on the crystal itself. You can see over here, there's a small crystal that as grains or microparticles land on the crystal, it measures the frequency change, and that can give you over time an accumulation rate of grains that continue to fall on it. For example, man-made disturbances of the surface, such as a robot moving by, or in the case of the CLPS mission, it wouldn't be a human at that point in time, but for robots moving by, or even micrometeorite disturbances, and even natural phenomena such as the phenomena that you see at the terminators at the sunset and sunrise, where there's this observed phenomena of dust grains arising at that time period. So first, it's a science mission to understand that phenomena, and then secondly, it's an engineering mission, because we want to, if we can understand the dust accumulation rates, for example, you can extrapolate that to understand how much dust you're going to have over a period of time landing on your solar panels or on your in your gears and whatnot. Again, just nothing more than a measurement mission. You can see here that this is the dust cover you see, and then inside it we've got it. We have to protect it on launch, and also protect it once the lander lands, so that that dust plume that's derived there is not going to contaminate it. And then we do the measurements. We've done vacuum chamber tests on it. Maybe I can show you this test here. This is kind of interesting. See if we get this will come up or not. So this is showing we put it in a vacuum, and we learned right away that we're going to have to cover it. This is a thermal vacuum chamber evacuating the air with the simulant in there. You can see how it right away it starts boiling up and saturated the crystal right away. So that's when we went to the dust cover. After a while, you'll see it get to an eruption boiling point. So from that, then we go into what we're doing with the ISRU technology. We're trying to, taking the dust, taking the simulants. We have a quarry here in Texas. We're located in San Antonio, Texas, and we have a quarry called the Canipa Quarry, and that's where we get our basalt simulant. It's not an exact match, but it's got the mechanical properties. It doesn't have the chemical properties, but it's very good for at least getting the first order of magnitude indication of what we can do with it in terms of melting it and turn it into stabilized material or solid material. We're also looking at it in terms of how we can turn it into an extrusion material as well. So we've been doing tests with some of these bricks that we've been making. Also laser seaming it down here at the bottom. You see some laser seams. We've taken a laser and try to seam the bricks together. And so when we started doing that, we started thinking about, well, how do we actually apply this? And we have two ways of doing this. We're doing brick forming, where we're actually melting it and turning it into through an induction heater, and then we'll be printing out the tiles for landing pad applications. You can see here, one of the applications we would do is to print these tiles, and they would be melded together on the sides, but then on the top end of it, they would be seamed together with the laser seam as well. So that's one of the things we're looking at in terms of how do we create these tiles for landing pad applications, or just road building, or even just dust mitigation, laying down a quick way to mitigate the dust as you in an activity where you're area of activity where you're doing setup of a base. One of the things we're doing, one of the things we're working with is a collaboration with Honeybee, where we're taking their planet back, and that's one of the way we acquire the fine grains out of the excavation material. Then we're doing extrusion layering. So we've been able to take the material, the basalt, and actually bind it with a PLA binder, and to produce a filament. And we're actually 3D printed. These blocks over here have been 3D printed with this basalt material. The ratio is 80% basalt to 20% PLA. So it's not a true ISRU. We want to start doing the binding and the 3D printing with filament. Not only filament, but also pellets that we create. Over here, we've been able to do the pellets in filament. Pellets will give you a bigger bead, the bigger nozzle that you could extrude out. And we want to get to about 50 millimeters in size, but in time by the time we get to printing out habitats. So with that, we have a 3D printer we're working on too. That's called a hang printer. I'll show you an image of that in a little while. Here. So one of the things we're also doing is we need to figure out the platform. So we're working on robotic platforms for hanging the induction heater itself, and also for the hang printer. Here's an example of what this hang printer technology is looking like. Let's see this image. This video comes up. So the idea for the hang printer is that we want to get away from a large gantry, heavy gantry, having to bring up a big, heavy bulky thing. This hang printer can be able to print from meters, from a meter to meters of size. We could hang it, for example, around that pit, at the edge of the pit, and we could print from the bottom up if we needed to, and put a structure that way, or even hang it from the walls of the lava tube caves as well, for printing inside the tubes. We have a test bed where we've taken our ElCat simulant, and we're doing this is mostly with our students, where they teach them how to make the robots, and their task is to figure out how to get into the pit, how to traverse the terrain, and learn how to get down in there, and with whatever concept they have. And there's all kinds of concepts they've come up with for getting down into the lunar pit. This is a picture of a notional example of the kind of the items that we would have to deal with, and the technologies that would be required in terms of excavation technologies and accumulation technologies of the regolith and the excavation of the fines to produce the pile, so the tiles. You see here the large mound here, and over here you see this roller. This is part of what we call these civil engineering processes. What are those processes for? And this is more of a traditional approach to building the foundation and a structure. But at the same time, I think it's important to understand that civil engineering aspect that goes into all for example, the underlayment has to go into before you start printing onto the lunar surface. How do you pack it down and do compactions? We've been doing compaction studies, and with a regular compressor, subvibrating compressor, we've taken our commercial ElCat soil, and then done some compaction testing, where we put on our test bed, we put a layer of I think it was a 2-inch depth of the loose fine soils, loose fine regolith or the simulant. Did some density testing on, and then the vibration test of the compactor. What we found on this one was first of all, the wheels were not the right traction to be using here. That was a bad design. But we found that the first run of the compactor really did do a pretty good job of compacting it, but it didn't get very far because of the traction of the wheels that got caught up in the dust accumulation. You see, I think in one of these images over here, all the dust that started just flying everywhere when it started moving. So those are more lesson learns. So here's the back to the melting technology. We just received an award from NASA, an STTR award, a phase 1 award, where they want us to take our melting technology and our nozzle. We have a proprietary nozzle that actually allows us to form the bricks in one step, and also place the bricks. So we need to combine the heater with the nozzle to produce this induction furnace nozzle in a one-step process, where we're actually acquiring the powdered fines, the powdered fines, forming the brick and placing the brick at the same time. And you can see here, this is one of the first solidified materials that came out of this furnace. So up in here, in terms of for the pavers that would come out to, this is our interlocking paver system. And again, the idea is that as this nozzle places the brick, the heat of the first brick and the heat of the second brick meld together, and then it moves to the third place, and the sides of these bricks are melded. And then, if you recall, I showed you that laser seaming. They would come back around the top and laser seam the top edges of it to get a cohesive surface. So we in Astroport, we're developing the portfolio of technologies. I mentioned there's a third process we have where we sinter the brick with that binder, but then we go back and reheat it, and we pull out the basalt, and we're left with a pure basalt brick. And that way we can 3D print it with some fine honeycomb shapes here. There's the printer, there's the other printer, and there's the laser seamer as part of those technologies. So we also think that our heater is going to be useful for volatile extraction. So we're, we don't only want to just use it for printing bricks, but we want also for extracting the volatiles, minerals out of the regolith. So we're doing tests in the volatile extraction with the Saltwater Research Institute down here in San Antonio. We're partners with them in a lot of these projects. And then we also are looking at lunar pit access here. So here's one concept we have here for how do you get down to the pit using a zipline concept. These pits are pretty deep. You saw some images earlier about the Tranquilitatis pit. That pit is about 100 meters in depth. This pit at the Marias Hills is about 60 meters in depth, or maybe even 45. I think that we recalculated that. That's 45 meters in depth. So it's a little bit easier to get down into, but still hard. And you can see here the scale. This is a scale model of it that would show how the tubes would kind of go from one side to the other side with the pit floor down here. I think I have a movie to show you if we have enough time. This is our LIDO mission that we're developing, the mission concept for how to get down to the Marias Hills and how do you approach it. We have a concept called green reconnaissance. The idea is that we don't want to get there and land there right next to the pit and with all the hydrazine or rocket blast and plume, just contaminating the pit before the scientists get in there with their instruments. So we call it green reconnaissance, where we would be able to land at some distance away from the pit and around, again, with some protective but natural features, and then traverse to the pit. It'd probably be a kilometer of distance, maybe a couple of kilometers. So that's going to be a challenge in itself to get to that pit with the ability to get down in there with the zip line concept. If I have some time, I'll show the video of the mission concept. It's about 5 minutes. Is there enough time there?
No, Sam, I'm sorry. To stay on track,
you can go to the website. There'll be a picture of it there, and you can find it there. xarc.com. It's pretty easy to get to. So that's this idea here is to really use the zip line to lower down the science instrument. And then it carries with it a spot, a robot dog. We call it a mule, multi-utilized legged explorer, and it goes into the cave, and it does its reconnaissance mapping of the cave with 3D LiDAR measurements, and it comes back and relays it back to the rover, and then that relays it back to Earth. And I think with that, well, there's some. So quickly, here are some habitat stuff we've been working on. This is more Mars type things, but we've been looking at habitat development again with 3D printing, and then looking at the interiors of how do you live with a crew of 4 in a real confined area. This is a 2-story situation here. We advanced from that to our Hexhab concept, which is a little bit more of a 3-story structure. This is part of the 3D challenge that NASA had, the 3D printed habitat challenge. This idea came in 4th. It didn't get to where the prize money was, but we did reach 4th place. The idea was to really outfit the whole habitat with all the environmental controls and mechanical aspects of the habitat. Understand how you build it out, and also the construction process had to be understood as well. Again, if you go to the website, you'll see a movie of it as well, and how that whole construction scenario works out. And then there's interior, pretty pictures here of the interior of the habitat. So the idea of the habitat of the 3 floors was that each floor had to be self-contained in case of a breach in the hull, or some sort of a catastrophe where one floor had to be evacuated. That each floor was self-contained and didn't have to rely on the systems from another floor. And it was designed that way purposely. That's why when you see a ladder or you see an elevator in the habitat, that's the reason for it. It was to be able to seal off each floor. Here's again, I'll show you the concept of that, the inflatable. We're looking on these foam inflatable tubes as a way to do the expansion, where it's packaged up in the rocket fairing here, and then with the floor panels, and then eventually it gets these inflatable tubes expanded out the two sides, and the floor panels themselves are automatically dispersed or get laid out as well. And so regolith porosity test is the gas part. We have to understand what's the porosity of the gas of the regolith. If we want to start filling up the pit with the dome, so that you understand, what the leak rate of gas. And when we talk about these putting domes on these pits, we're talking about 132 cubic meters of pit volume. So that's going to be a lot of gas. And how are you going to create that gas? How are you going to do that? Where's the process for doing all that? It's a lot. That's why it's all a long ways down the road before we get to carving these domes. Just real quick here, I'm going to end here. This is ElCats, or part of what we do. All those technologies that you saw there, we give those same challenges to our students, and they go out and they use the LiftPort program as the framework for what they are charged to go and solve for us as well. So they go into caves here in area. So they take, for example, they take science measurements and instruments, and they take them into the caves here around the area, and so they can do field tests, and they learn about exploring these environments as well. So it's a real good, successful program, and really we've been attracted for the last 5 years, and we've seen students go from not knowing what they wanted to be to now they're in college right now in aerospace careers and aerospace majors. So the idea was to give them the remote sensing project. That's the first year of the project. They got to commit to the program for 3 years. The first year they're doing remote sensing. The second year they're doing the reconnaissance robotics type stuff. And the third year they're doing the space architecture applications. And then the fourth year they actually make a comic book. It's going to be, the first comic book's going to be printed this summer. That actually is a comic book of their experience as well. So for publication. And that just shows they do balloon launches, and that's just a kind of a curriculum. It's a little busy chart. And with that, I'm done. I think that's it.
Thank you very much, Sam. There's so much in there. If I were to redo my career and go back in time, I think space architect might have been the path I took. So I'm fascinated by that. I want to talk to you kind of offline about a couple of these things. This is terrific.
Yeah, it's been fun.
We do need to move on to get back on track. So thanks a lot, Sam. Really appreciate it.